Conceptual Introduction to Linear Regression, Part 6, another way of thinking about correlation and R squared. As with everything in this presentation, this will be a super quick overview due to limited time, so please see me if you want more detail. Suppose we have some data that I'm calling x and y, and I'm going to show a feature of the data that is useful to think about sometimes, the sum of the products of these two variables. So, on the screen, I've computed the product of x and y for each observation. There's only 5 observations. And at the bottom, I've added those products together. The sum of the products is 6. Consider, if you kept x the same, how could you rearrange y to maximize the sum of the products? How could you rearrange y to get the most negative sum of the products? Here's a pair of variables with a perfect correlation. Notice that the biggest values on x correspond to the biggest values on y, and the smallest values of x correspond to the smallest values of y. Let's try doing sum of products on this. It comes out to 10. That's more than when the numbers were arranged differently. It turns out this is the maximum sum of products that you can get with these x's and these y's, because the biggest x's go along with the biggest y's, and the smallest x's go along with the smallest y's. That's how you would rearrange any data set in order to maximize the sum of the products. Put the biggest values of one variable alongside the biggest values of the other variable. If we divide this result by the degrees of freedom, we get 2.5, the covariance. And this works because both variables are centered around 0 already. The formula for the covariance between x and y is shown on the screen. It's what you would get if you centered x and y around their means, then took their product, and added all those products up, and then divided by n minus 1. Variance is like the covariance of a variable with itself, then. If I duplicate x and I calculate the sum of the products, then I end up with 2.5. Well, I end up with 10, and then when I divide by n minus 1, I end up with 2.5. So you can see this relationship in the familiar variance formula. It is analogous to the covariance formula. So the typical way we write variance is x minus the mean of x squared, and then add all of them up and then divide by n minus 1. But I can rewrite that as the sum of x minus the mean of x times x minus the mean of x, all divided by n minus 1. And then it's the same as covariance, except I've got x twice instead of x on the one side and y on the other side. Correlation is supposed to measure the strength of the relationship on a standardized scale from -1 to 1. And we already know that covariance seems to get at how much the variables vary together, the strength of their relationship. It's maximized when all the biggest values on one variable go along with all the biggest values on the other variable, because that's how you get the largest possible sum of products. We see that the value of covariance can be bigger than 1, and in fact, it would get bigger if the units of the variables were situated such that the overall variance of the values got bigger. So correlation is like a measure of the covariance relative to the variance, how much they vary together compared to how much they vary separately. R squared, the coefficient of determination, is related to this. We call it the proportion of variance explained, and I wanted to show why this sort of makes sense from a different angle with all this covariance explanation. So here's the formula for R squared. It's the same as the formula we already saw for the correlation here, which is the covariance divided by the square root of the products of the two variances. The R squared is the same as the formula for the correlation, except that, of course, everything is squared. So now it's the covariance squared divided by the products of the two variances. I'm going to rewrite the numerator for symmetry. Now it shows the covariance of x and y times the covariance of x and y, multiplying by itself is what squaring is, divided by the variance of x times the variance of y, to illustrate that this value is like the proportion of the variance in one variable that is explained by its covariance with the other variable. You can also think of this as the covariance divided by the variance of x multiplied by the covariance divided by the variance of y.